This is the video abstract for our paper entitled Conditional Random Matrix Ensembles and the Stability of Dynamical Systems. Networks appear throughout physics, and throughout nature too. In short, networks are everywhere. So we need to understand their robustness and stability properties. The global financial crisis provides a stark illustration. The global financial system can be represented as a network, where banks are nodes and the link between them represent transactions. Sometimes banks fail, with knock-on effects for the whole network. Network structure affects the stability of complex dynamical systems like the financial network. We need to understand how. Throughout, we will illustrate using ecological networks, which are used to represent interactions between species. These networks can be represented as matrices. Interactions can be given positive or negative signs, according to whether they are beneficial or detrimental, as well as numerical values to indicate interaction strength. We wish to determine if systems such as these have stable or unstable equilibria. Unstable stationary states are sensitive to even tiny perturbations. Stable stationary states are robust to small perturbations. Stability can be assessed by finding the eigenvalues of the dynamical system's Jacobian matrix, evaluated at the equilibrium point. An equilibrium is stable if, and only if, all of the eigenvalues of the Jacobian have negative real part. To determine what happens to the stability of systems as they grow large or complex, it is common to consider random distributions of Jacobian matrices. For each element, we toss a coin whose probability of a head is C. If we get a tail, we fill in the entry with a 0. If we get a head, we draw a sample from a standard normal distribution. We repeat in this way until we have filled in all of the elements of the matrix. For matrices constructed in this way, it can be shown that the probability of having all negative eigenvalues tends to 0 as the matrix grows large. This led to the conclusion that large, complex systems are highly unlikely to be stable. However, this construction makes some strong assumptions. The first assumption is that there are no dependencies between the entries in the Jacobian matrix. The second is that all of the non-zero entries of the Jacobian matrix are identically distributed. But recall that the matrix entries are meant to correspond to interaction strengths in real networks. These interaction strengths will have particular properties specific to their real-world context. If the random matrix distribution does not accurately reflect the real world, we will draw erroneous conclusions about stability. In our paper, we show that we can get better approximations of stability probability by conditioning on realistic system architectures. We demonstrate that some systems can grow arbitrarily large and still possess a stability probability of 1. One example of this is given by an extension of the SEIR model of disease transmission. Our extension allows arbitrarily many subpopulations of infective individuals, allowing us to consider arbitrarily large SEIR networks and to demonstrate that stability persists. In conclusion, wherever networks have been used in physics, the use of random matrix ensembles has usually followed. But whether regarding the stability of dynamical systems or any other topic of investigation, conclusions obtained using random matrix theory will only be as sensible as the choice of random matrix ensemble. And choosing a random matrix ensemble for mathematical convenience alone is liable to lead to misleading conclusions.